that we have so many interesting speakers, and we have Juan Antonio de la Fuente Bencomo and Salvador Suarez Garcia from the Canary Islands, Barry Usagawa from the Board of Water Supply, Eugene Tion from Department of Business Economic Development, and Manfred Zapka, who's an independent consultant. And I want to thank all of you who've registered and have joined us today. And this should be a very interesting session. So I'm just going to hand it back to you, Stan.
All right, thanks, Michael. And just for an administrative note, if you're not doing a presentation, could you please go on mute so that we eliminate as much of the background noise as we can? And welcome to the Canary Islands Hawaii Freshwater Forum. And thanks to the State Energy Office for helping us put this on today. This is an effort by Renew and Rebuild Hawaii, which is trying to promote renewable energy and sustainability across the state of Hawaii. And we like to go across the planet, and we found that the Canary Islands was very, very much like Hawaii in terms of tourism, separated islands, not near mainland, requiring a lot of fossil fuel in their energy plan. So many things in common, but they handle some of their water issues a little bit differently. So we wanted to tap them and see what they have. Whoever that is in the background, could you please go on mute? Okay. So first up, we have Dr. Salvador Suarez Garcia, who has a presentation, and he is the head of the Institute of Technology for Renewable Energy in Canary Islands. So, sir, it's all yours if you want to take charge of the screen.
Thank you, Stanley. First, I would like to thank you for your kind invitation to participate. For us, it's our honor to be here with you, sharing experiences with Hawaii. So I go now to the presentation. Let's see if I can share can you see it now?
So we can see it?
Yes. Stanley, can you see the screen, my presentation?
Yes.
Yes. Let me put it full screen. You can see it now, right?
Yes.
Okay, yes. So I'll try to go fast because we have a very short time. Try to cover all the slides in 10 minutes, okay? Well, the Canary Islands, it's an archipelago of the coast of North Africa, belonging to Spain. And here in the Canary Islands, well, we have our institute that belongs to the regional government of the Canary Island. In my case, I'm in the Renewable Energy Department. Our activity is very focused on technical solutions for trying to maximize renewable, variable, and intermittent renewable energy penetration in weak and small electrical island systems. We have been sharing our experience with many European island regions, and we are also supporting efforts by the European Commission, by the Spanish central government, the government of the Canary Islands, to transfer clean energy technologies, especially to less developed countries of the Western African coast. We're very active in Cape Verde, Senegal, Mauritania, Morocco. And also we are advising the regional government in the definition of regional energy policies, especially the ones dealing with the promotion of renewable energies and energy efficiency. Our main focus deals with technical aspects of penetrating with renewable energies in island electrical systems. I mean, we are faced with many barriers. Some of them, of course, they have to do with the economics of renewables. They need a high initial investment, and this sometimes is difficult to find. Also, the territorial planning is very important because, at least in the Canary Islands, we're facing a lot of restrictions from air safety, from special birds areas, also from national parks. 60% of the territory of the Canary Islands is highly protected. So, I mean, there's also some land issues there, but our main activity has to do with barriers associated to the electrical island systems. Again, we're approaching solutions with a very comprehensive strategy that combines 5 elements. We are working on forecasting through climate modeling. We're working on grid stability also to try to determine maximum levels, admissible levels of renewable energy penetration, also doing demand side management of those non-critical, manageable, dispatchable loads. Working also on distributed generation, trying to generate clean energy close to where the consumption is of the energy is located. And then the most interesting aspect that has to do with energy storage is the enabler, the key enabler for trying to increase renewable energy penetration. So let me look at what we are doing in each of these elements. In energy forecasting, we are using climate numerical models, basically WRF, in combination with a statistical modeling, and also with satellite imaging to try to get very reliable forecasting 1 day ahead, but also short term and nowcasting of wind and solar conditions to try to determine what the production of wind and PV facilities will be able to generate. Try to give in the dispatching in the scheduling of the unit commitments for trying to cover demand of electricity in our islands, trying to give priority to renewable energies. Then grid analysis. We have a group of colleagues with more than 15 years experience modeling with which is the standard for those electrical engineers. Maybe you're familiarized with this. It's the standard tool for doing grid stability analysis is from Siemens, is the PSSE modeling tool. And we are doing dynamic modeling of our island electrical grids. We also have been doing work outside the Canary Islands, a grid extension in Mexico. We also help with the integration of a combined cycle in Israel, in a part of the country with weak electrical grids. But we're mainly doing work on grid stability in these scenarios, have high renewable energy penetrations, to try to determine maximum levels of penetration and how to reinforce the grids to try to achieve those goals of increasing even more our renewable energy supply. And then energy storage. Energy storage, I'm going to tell you about an experience we have in the smallest of the Canary Islands. It's called El Hierro. It's an island with a population of about 10,000 people with a peak load of 8.5 megawatt. And what we have done, if we have installed in the island a wind farm of 5 wind turbines, each of 2.3 megawatts. It's the Enercon E70 wind turbine for a combined power of 10.5 megawatt. And we are supplying the island loads from this wind farm when we have excess electricity. Well, what we also have done besides installing this wind farm, we have gone up in the hills. There was a natural crater that has been waterproofed at 700 meters of height. And we have built a lower reservoir at sea level. And what we do is that we have connected by stocks these two reservoirs. And what we do is when we have excess wind from the wind farm, we take this electricity to the pumping station and bring water up to the upper reservoir and store in potential energy. And when there's no wind or we're experiencing a peak demand in the load of the island, then what we do is we let water come down from the upper reservoir to the lower one, and we turbine this water to provide that power that the wind farm is not able to supply. Then, hold on, please. Yeah. Then what we have, well, as you can see here, we're covering about 60% of the yearly electricity demand, I mean, in the yearly balance, okay? In the summer months, when we have higher speeds of wind, we have been able to operate the system for a couple of months, 100% only on wind, supplying, covering all the loads of electrical loads of the island, only from the wind farm. Then we, for more flexible storage solutions, we have been looking at different battery technologies, lithium-ion, but we also are looking with interest to hydrogen. Hydrogen as a means of storing excess electricity from the renewable energy systems installed in the island, but also hydrogen as an energy carrier, allowing to put wind and solar inside, for example, transport vehicles. We have these two experiences the first two electrolyzers in the Canary Islands back in 2007. What we did was in one of them, try to emulate what the demand of a small isolated community. We had a dissipating load, a programmable dissipating load that where we were somehow simulating the demand of the island. And when we have also a wind farm supplying electricity to an electrolyzer. And what we used was hydrogen technologies to stabilize this small microgrid. We had a 1 kilogram an hour electrolyzer, 50 kilograms of hydrogen storage capacity, and with these hydrogen and 6 fuel cells, providing 30 kilowatt of three-phase electricity to the dissipating programmable load. And then we also have this experience on using hydrogen as an energy carrier with a small vehicle powered by hydrogen produced by a small hybrid systems of 3 kilowatt peak in combination with a 7 kilowatt wind turbine, supplying electricity to an electrolyzer we brought from California, from Proton Energy, the Hagen, producing very pure hydrogen, 6 nines, 99.9999 purity hydrogen with a PEM electrolyzer, and then we compress with a booster compressor to 200 bar to supply this small vehicle. Currently, we are installing we just finished installing an electrolyzer of production of 11 normal cubic meters of hydrogen an hour, and the idea is to stabilize a small microgrid covering the energy supply to this cattle farm we have in the northwest of the island. We are providing from a hybrid PV wind hybrid system using batteries for primary regulation and the hydrogen for longer term storage. We are providing 100% rest capacity to cover all the electricity demand from this farm. And then we're looking to more sophisticated work, okay? Because hydrogen is nice, but has limitations, okay? So when you want to, for example, provide hydrogen to a small vehicle, 5 kilograms of hydrogen can give you maybe 500 kilometers of autonomy, and storing 5 kilograms of hydrogen at 700 bar can be done. But the different story is when you want to go from islands like Tenerife and Gran Canaria, maybe 100 kilometers apart, and you want to have a round trip boat ship going from one island to the other, maybe you might need 10 tons of hydrogen, and storing 10 tons at 700 bar is complicated. So we're looking at trying to do downstreaming, try to get green hydrogen from electrolysis of water, and also nitrogen from the air. 79% of the air is nitrogen, and this syngas of hydrogen and nitrogen, taking this syngas to a Haber-Bosch process for synthesizing ammonia. And why ammonia? Because ammonia, you can have it in liquid at ambient temperatures of the Canary Islands at 27 degrees Celsius. You can have ammonia liquid at 10 bar. You could have it liquid at 0 bar, but then you would have to go to Siberia at minus 33 degrees, okay? But in the Canary Islands, you need to apply small pressure, 10 bar. Better than 700 bar in hydrogen. Even at 700 bar, hydrogen is still a gas. At 10 bar, ammonia is liquid, okay? So for logistics, it's better to work with ammonia. This is a project we are now engaging. We have the tenders now gone for the electrolyzer, the nitrogen production, and also the Haber-Bosch process for it's a demo, okay, to validate a proof of concept. We will be producing 5 kilograms of ammonia an hour with an off-grid standalone system powered by PV and a small power, wind power, okay? And the idea also is to have a pure hydrogen for a bus. We have called this project the Bio-Greenfinery. It's basically a refinery powered totally by 100% RES hybrid system. Then we have, with respect to distributed generation, a very interesting experience in one of the other islands in the Canary Islands called La Gomera. Okay, it's a different approach from El Hierro. El Hierro is a very centralized system with a big wind farm, well, big relatively to the island, the size of the island, and with a reverse pump hydro system integrated to the wind farm. Here in La Gomera, we're totally looking at a totally different paradigm. We're talking about going to 64 small microgrids to supply power to all these small communities at the end of the distribution lines grid of the island. There's no transmission, it's only distribution at 20 kilovolt. Okay, so we will have these small microgrids powered by PV, also with energy storage capacity, able to provide ancillary services also to work on the grid and the grid balancing of the total island supply. Okay. And as said, we will have in the Canary Islands, these two islands, one powered by a central system, another totally decentralized approach. And then we're also looking at new things, okay, offshore wind. The Canary Islands, I mean, is blessed by the wind conditions. We have this very good wind blowing northeast, it's called the trade winds, and they encounter an island like Gran Canaria with a very complex terrain, and the wind accelerates in the southeast of the island. And there we have an average speed of 11 meters per second, but very constant wind. We can have wind farms there with capacity factors of 60%, more than 6,000 hours a year. This is, I mean, I guess at least the best site in Europe, maybe one of the best in the world, okay? With very constant wind, good winds, and we are doing a spatial planning. We're also doing preliminary design and assessments of economic feasibility of wind farms in this area. And then we have, as part of the work we do for the regional government, we have designed the strategy to achieve the goal of the Canary Islands, is total decarbonization of the energy system by 2040. We have elaborated a set of 8 very comprehensive strategies covering different areas, PV, energy storage, electromobility, geothermal, and these strategies are supporting this Canary Island energy plan, which you can access. I mean, we can give you access to all these tools, although they are written in Spanish, okay? But you can have access to all these strategies. And as an example of what we have been doing, we have been using either, for example, to try to assess potential of all roofs, not only in the residential, but also industrial, tourist sector, looking at the slope of the roofs, also obstacles, and try to assess. And we have determined in the case of PV that we would be able to dispose of space to set 12,000 megawatt peak of PV, but we are happy with 1,200 megawatt. Okay, this is our goal for 2040.
Aloha, welcome to Anaheim McDonald's. Will you be using your mobile app?
Hey, please mute your mic at McDonald's. Thank you.
Go ahead.
Okay.
Can I just get a hash brown? Okay. Thank you.
Okay.
Thank you.
So this is part of the work we have done. This is also a slide just showing what we are doing also in the planning of the electromobility. We're planning to go to total electromobility by 2040, but with also a goal at 2030 of 225,000 units of vehicles. But by 2040, we will have to go from the 9,000 gigawatt hour currently consuming our islands up to 16,000. So we will be adding like something like 6,000 gigawatt more of electricity consumption, okay, from 9,000 to 15,000, sorry, okay? So, I mean, all this energy will have to be supplied by new installed renewable energy power, okay? And then this is an element that's we are trying to support, because there's no possibility of deploying this system if we don't have properly trained personnel in our islands. So we are also supporting the training in design, installation, operation, maintenance of renewable energy systems, and looking at the possibility of synergies between all these policies for fast energy transition with the possibility of promoting also green jobs in our islands, okay? So, I mean, and this is all driven by a series of issues like, I mean, the need for a fast transition, also the policies for promoting especially rooftop PV in our islands, and the need for electromobility. Electromobility that for us, we see it also not only as an opportunity for substituting fossil fuels, but also the possibility of using electric cars as a non-critical dispatchable load for supporting grid balancing in those scenarios of high renewable variable and intermittent renewable energy penetration, okay? We would need to do grid balancing in order to maintain grid parameters like frequency, voltage. I mean, electricity has to be consumed instantaneously, and if you don't have a load that either to store or either to consume, then you will have to curtail generation from renewables, affecting the internal rate of return of all those projects that have been financed, considering a capacity factor, a number of hours a year. And if you begin to apply curtailment, you will be affecting the financial feasibility of all these renewable energy projects. So, I mean, the idea is to use these non-critical loads also to try to minimize curtailment of renewable energy systems. And yet now to finish all the activity we're doing abroad, as we mentioned, we have been doing in Israel, Mexico. This year we also did the energy planning of Galapagos in Ecuador. We also are supporting in a European project. We're collaborating with Indonesia, Vietnam, and Thailand with universities there, trying to reinforce the curricula in the masters of renewable energies. And yeah, we are especially very active in the Western African coast. Okay, thank you for your attention. I'm sorry if I exceeded the sign time, Stanley, okay?
That's okay, Dr. Garcia, but I was afraid Michael might worry that I would hijack the conversation around hydrogen and make your presentation go even longer. But I just wanted to point out for the audience that one of the reasons we focused on the energy piece up front is that Canary Islands does use desalination for quite a bit of their water, and that requires energy, and they want to make it clean energy. They have a very high focus on reducing fossil fuel consumption, because just like Hawaii, they are highly dependent on fossil fuels, or have been over the years, and they've been very aggressive about eliminating fossil fuels from their energy production. I did have two questions for you though, sir. Number one, what's the depth of the water offshore where your wind turbines are?
Yeah, we're looking, I mean, because we have the same volcanic origin as Hawaii, so you get a little bit out of the sea coast and you begin to find yourself with very complicated bathymetry, okay? So in the case of this area in the southeast of the Canary Islands, at 8 kilometers, we are maybe at 600 meters, and then when we go out to 10 kilometers, we are facing 1,000, okay? But there are so, especially Norwegian, a Norwegian, very important Norwegian company that is interested, and they have technology. They come from the oil business, of course, and they have technology to take floating wind farms to 1,000 meters deep bathymetry. Okay. So, I mean, it's a problem. I mean, we wish we could have better conditions. I mean, not those depth, but I mean, we have technology today that can go to 1,000 meters. That's what they tell us, okay? The big corporations interested in developing these sites.
Okay. My second question is, have you looked very much into geothermal because of your also your geology?
Right. Yeah. Geothermal is of interest, of course. We have resources in the island of La Palma, which recently maybe you saw on the news. Volcanic activity in the Canary Islands was in this island, La Palma. So there's half a big resource there. Then in Tenerife and in Gran Canaria, those are the two big capital islands. There are also possibilities to develop, and it's a very interesting technology, because I mean, instead of having dependent on these intermittent and variable conditions of wind and so on, especially at night, we don't be able to produce PV, but the geothermal, the interesting thing is that it's totally manageable, dispatchable, and can be, but then again, I mean, this is also because you have high investment, and you will need to operate these geothermal facilities with a capacity factor, maybe, I don't know, 8,000 hours a year, and then, well, it will be complicated if you have too much wind and solar, okay, because maybe you will have to give more participation to geothermal, and so this is something that will depend also on when the technology develops in the Canary Islands, because there's too much uncertainty given the, but I mean, we will see, okay? But plans are to develop fully PV and wind, okay?
Okay, so it sounds like you've actually kind of focused on the intermittent renewables, wind and solar right now, and they're meeting your needs. So there's not really, you know, you have to go to scale to go to geothermal. So that would be an expensive investment when you've already invested heavily in solar and wind.
Right.
Okay.
Yeah. The good thing about wind and PV is that they have already advanced a lot in the cost curve. Okay, so they are very competitive, very mature. So it's time to invest in PV and wind. Maybe geothermal and even electric vehicles now are affordable, and maybe leave technologies that are not so mature, like hydrogen, maybe the offshore wind, after 2030. Okay, but
Okay.
from the period up to 2030, we want to focus more on more competitive, cost competitive technologies like PV and wind. Yeah.
Okay, thank you, Doctor. And if you can stop sharing your screen, we're gonna head into Mr. Juan Antonio de la Fuente Bencomo's presentation. And if anyone else has questions, could you please put them in the chat, and we'll pass them on to Dr. Garcia a little bit later on. Thank you, Dr. Garcia.
Okay, you're welcome, Stanley, for the opportunity. It's a pleasure to participate.
Thank you. Okay, Juan Antonio, it's all yours.
Now I was mute. So I guess if you can see my screen
Yes, your slides are up.
in presentation mode. Yeah.
Getting there. There it is. Now it's presentation mode.
So I'm going to explain the water site in the Canary Islands. This is the index I will try to follow. I will be quick because the time is short. I will skip the first part because my colleague Salvador has introduced the Canary Islands Institute of Technology. Just to say that our facilities in the southeast of Gran Canaria are an ideal platform for testing all the different combinations between desalination technologies and renewable energy sources. The ITC has carried out R&D activities in the field of renewable energy-driven desalination since 1996. We have actually tested more than 20 pilot systems in our testing facilities. The ITC Water Department was created in 2003 and participates in many different large European and regional R&D projects, mainly focused on energy efficient water desalination, decentralized wastewater treatments, the water quality evaluation and improvement. We have a very well equipped laboratory, and of course the use of renewable energy in the water cycle. Here you can see some particularities of the Canary Islands. The archipelago is formed by 8 islands with more than 2.2 million inhabitants and a surface close to 7,500 square kilometers. We receive every year more than 13 million tourists. Our economy is mainly based on the tertiary sector, and we have more than 140 natural protected areas. Here I will explain some conditioning factors in the water sector for the Canary Islands. I'm sorry for the image, it's in Spanish, but I will explain mainly the challenges we face into 2 groups. The cross-cutting challenges, we will see the population growth and the tourism boom that we have suffered in the last 50 years, and the specific challenges such as water resources scarcity, increased water consumption, and an incipient aridity and desertification in the whole archipelago. Here you can see how the population has increased since 1960 to 2018. We have passed from less than 1 million people to more than 2.1 million people. Also, the number of hotels and the millions of tourists have grown exponentially. You can see in the graphs. On the other hand, the water resources, both groundwater and surface water resources, have been reduced in the last years. And here we have the increased water consumption. We have divided the total volume of registered and distributed water into 3 different volumes. The first one has increased, has almost double the volume of water in the households in the last years, the last 20 years, from 1996 to 2016. The municipal consumption has also doubled the volume of water. but on the contrary, the economic sectors has slightly decreased. And the last specific challenge is the incipient aridity and the certification of the islands. Also, islands that had lots of water in the past, like La Palma, La Gomera, are now facing some water scarcities. So this is an incipient problem. We find widespread decrease in rainfall in all the archipelago, together with an increased water temperature and the rise in sea levels. Well, the water resources availability in the Canary Islands, historically, Canary Islands have suffered the water scarcity mainly due to the low rainfall, the high permeability of soils, and of course, the overexploitation of the aquifer resources. We will see in an image how in the island of Gran Canaria, for 100 years, the aquifers have been overexploited, and for that reason, they have suffered the sea intrusion. Well, the conventional and non-conventional solutions that we have applied, we found a groundwater catchment by two types of catchments. One of it is the horizontal water tunnels, that is what we call here the galerías, you can see in the image below, and together with vertical wells. Also the drinking water catchment and storage, the construction and waterproofing of reservoirs. Of course, an efficient use of water is needed, and in the last years, the desalination and reclaimed water reuse. Well, desalination in the Canary Islands, the archipelago is an European reference in desalination. The first seawater desalination plant in Europe was installed in the island of Lanzarote in 1964. Currently, freshwater total demand stands up to 200 cubic hectometers per year. We have a desalination installed capacity of more than 700,000 cubic meters per day. That means approximately 2% of the world installed capacity of desalination. Here we have installed all the desalination technologies, both thermal technologies and membrane-based technologies. And you can see in the image the production capacities installed. The main one is seawater desalination with 167 plants, brackish water, and reclaimed water. Well, the origin of desalination in the Canary Islands, we have almost 60 years of experience in desalination by thermal processes. The first plant installed, as I told before, was in Arrecife, Lanzarote in 1964. 5 years later, we installed in Las Palmas, in Gran Canaria, another MSF plant in 1969. I would like you to see in the next image, this is the image of 1969 of the MSF plant in Las Palmas of 20,000 cubic meters per day of production capacity. And in the next image, you will see the same place, but actually nowadays. This is now seawater reverse osmosis plant. It's called Las Palmas 3. It's the biggest, the largest desalination plant in Canary Islands. It has a production capacity of more than 100,000 cubic meters per day. And in the image you can see a project that we have recently done for a floating PV system that will go inside the intake pond of the seawater intake pond of the desalination plant. So almost 40 years of membrane desalination. We have left back the thermal desalination, and now we're operating mainly reverse osmosis. The first seawater reverse osmosis desalination plant was also installed in Lanzarote. 6 years after that, they installed Las Palmas 3 desalination plant. At the beginning, it had a production capacity of 36,000 cubic meters per day, and actually we have more than 100,000 cubic meters per day. Here you can see the role of the non-conventional water resources. In this case, we found that groundwaters and surface waters have been decreasing along the last years, and in the other side, desalination and reclaimed water have been increased. You can see the same graph in another way, and you can observe that desalination and reclaimed water are turning the main water resources nowadays in the Canary Islands. You can see the role of desalination. More than 70% of the water for human consumption in the islands comes from desalination plants. As you can see in the image, main water resource in the islands of Lanzarote and Fuerteventura. In Lanzarote is close to 100% of the water availability depends on desalination plants. It is an alternative to a scarcity of natural water sources in the islands of Gran Canaria with more than 50%, and in El Hierro with more than 40%, and in the island of Tenerife it means more than 16%, but it's increasing in the last years. Water desalination is linked with blue economy, is directly linked because the social and economic stability of the Canary Islands have been possible thanks to the supply of almost 2 million inhabitants per year and more than 14 million tourists with desalinated water, and also a multitude of agricultural hectares, both with desalinated and reclaimed water. The installed capacity, as told before, is more than 730,000 cubic meters per day. We can see the different desalination plants. The main desalination installed capacity is in the eastern island, that means Las Palmas, Lanzarote and Fuerteventura, while in the western islands, the province of Santa Cruz de Tenerife has the lowest density of desalination plants installed. In this image, you will take a general view of how, which is the problem that we have faced. We will see how we have the evolution of the groundwater extraction in the island of Gran Canaria. Okay, we will see. Pay attention, please, to the blue dots that are the groundwater extraction without marine intrusion. Then you will see how the orange dots came on the map. Those mean the groundwater extraction with marine intrusion, and finally the yellow dots that mean the groundwater extraction that have been dried or abandoned because it turned on salty water. And finally the desalination plants, both for brackish and seawater desalination. So we can see in 100 years from 1904 to 2004 what has happened in Gran Canaria. You can see in 1964 how we can observe that groundwater extraction begins to have marine intrusion, and from 1964 to 1984 desalination appeared in the scenario of the water resource here in Gran Canaria. Here we can see the role of desalination in the island of Gran Canaria. It has increased exponentially in the last years. As I told before, in 1984, desalination was declared to be of general priority and an urgent interest in the island, in the archipelago, and it began the startup of the Canary Islands desalination program. Now we are going to have a general view of reclaimed water reuse network in the island of Gran Canaria, just to see that it goes from the north to the south to southeast of the island. The coastal wastewater treated and reclaimed water reuse balance in Gran Canaria means that we treat more than 90% of the wastewater, and from this 90%, 35% is reclaimed water that is reused in agriculture. In the distribution network that goes from north to south in the island, we find up to 27 wastewater treatment plants, 6 tertiary treatments, mainly reverse osmosis is used for these treatments, 25 pumping stations, 41 water storage tanks, more than 300 kilometers of distribution network for this reclaimed water, and more than 2,000 users of this resource. Well, the water energy nexus in the Canary Islands is as important as complex to manage. The water managers incurring very important energy costs and therefore economic cost due to the high demand in electricity that reverse osmosis has. There is an increasing dependence on industrial water production, as we have seen before. A figure to take into account is the integrated water cycle in general in the islands can account to 20% of the energy demand. This will be in function of the island and, of course, of the desalination installed capacity. Just to get a glance, in Lanzarote, you have the biggest energy demand in public facilities for desalination, followed by Fuerteventura, El Hierro, and Gran Canaria. Here you can see the energy dependency on the industrial water cycle. You can again observe that the main energy demand is by desalination production. It's up to close to 6% of the energy put on the grid. Also, again, desalination plants get the most higher figures for the contracted power, the energy consumption, and the cost in euros per year, followed by the pumping stations, and after that, the water treatment plant, wastewater treatment plants. I would now like to introduce briefly the Desert Plus Living Lab platform. This is a Macronesian platform in order to increase the excellence in R&D, in water desalination, and knowledge of the desalinated water energy nexus linked to the blue economy. This is an instrument that will help us to go from being a global laboratory in desalination to an international living lab of R&D in desalination. ITC coordinates this living lab, and within the living lab we offer technical and logistic support for the installation and testing of prototypes and new devices, and mainly focus on desalination and the use of renewable energy for driving desalination plants. The technical support and consultancy for the development, upscaling, and demonstration in real conditions of innovative solutions using local scale desalination open infrastructure that we have within the desalination living lab. And of course, we also offer training activities, educational programs, knowledge and technology transfer of desalination and the use of renewables. Well, the Canarian innovation in the water sector, we find different aspects. The first one is the reduction of e-person in water and other harmful elements. Of course, the reduction of fossil fuels consumption and the promotion of the use of clean energies such as solar photovoltaic and wind energy. In the last year, we're looking also to the wave energy. We have few projects, ongoing projects, that are looking to wave energy converters in order to get energy for driving desalination plants. We also look to the development of intelligent software for better water management in the production plants. Of course, as I said before, the water reuse for agriculture, reclaimed water. The natural wastewater treatment by artificial wetlands. And as I told before the webinar, the joint management of water between the different municipalities. It was we call Mancomunidad, the community of municipalities. We have a very big Mancomunity here in the southeast of Gran Canaria that works very well, managing the whole, the integral water cycle. They desalinate water, they treat the wastewater, and they give reclaimed water, and they distribute the water to the final users. Well, another very important aspect is a research line we have within the water department is the energy efficiency improvement in desalination. You can see in the graph that we have moved in the last 40 years from the thermal technologies with very high specific energy consumptions. We can't compare electrical consumption with thermal consumption, but we can see that we have lowered in the last years from more than 20 kilowatt hour per cubic meter to around 2 kilowatt hour per cubic meter. We have now in our facilities a desalination plan of 100 cubic meters per day of installed capacity that is below the 2 kilowatt hour per cubic meter. We will see later the energy cover device that we're using. Well, the Canary Islands is like an energy cover devices test room. We have tested all the energy cover devices available in the market. We started in Las Palmas 3 with the Francis turbines. In that year, we had an energy consumption of more than 6 kilowatt hour per cubic meter. After that, we have tested also turbocharger in other desalination plants. Nowadays, very few desalination plants work with Pelton turbine. Aqualink, we also know the case of one plant in the south of Gran Canaria that used this energy recovery device. We also tested the aerokinetic energy recovery device. This is a patent of a Canary Islands engineer. We have tested this system in our facilities, and we achieve specific energy consumptions around 2.2 kilowatt hour per cubic meter. And the last energy recovery device we are actually testing in our facilities is the Salino. Salino, we have achieved specific energy consumptions below the 2 kilowatt hours, and is a very compact system that has the high pressure pump, the energy recovery device itself, the booster pump, and the electrical motor in the same device. It is especially interesting for compact desalination plants installed inside a container, a 20-feet container.
And Juan Antonio, we do just have a couple of questions for you when you're finished up. Thank you.
Okay. I'm finishing in a few minutes. We also take care of the brine discharge. We try to get a minimum impact of the brines, and we also take care of the brines valorization. Together with Canary companies, ITC has developed the Venturi diffuser. This diffuser helps, it maximizes the dilution of the brine before discharging it into the sea, back to the sea. We also cultivate microalgae with the brine from our desalination plants. Our colleagues in the biotechnology department use our brine from the desalination plants we have in Pozo Izquierdo in order to cultivate microalgae, and we have a laboratory scale test to obtain value-added byproducts. They cultivate, for example, Dulnanella salina, and they get beta-carotene and other byproducts that have a very high value added in the market. So the high innovation in water purification, desalination, advanced treatments as a quality requirement. Here you can see in this picture a wetland. Well, 90% of the Canary Islands has a sanitation network. Also using membrane bioreactors in wastewater treatment plants, paying attention to emerging and priority pollutants, more than 20 natural purification systems in operation without energy consumption or very low energy consumption, mainly in rural areas, and demonstration of orchards with various irrigation techniques, all with reclaimed water. Some featured innovations in the water industry. When we make a design, we use last generation reverse osmosis membranes with higher fluxes and higher state rejection. We also put into the pressure vessels membrane hybridization in order to compensate the hydraulics within the pressure vessel. And of course, we use high boron reaction reverse osmosis membranes. The use of ultrafiltration when you have a desalination plant with an open seawater intake is interesting also. Only use of antiscalants, this you can only be done when you have a very good seawater intake by beach well, as we have in Pozo Izquierdo. We try to find the maximum energy efficiency by using different energy recovery systems, the optimized hydraulic designs, also using variable speed drives in pumpings. We have patented process of calcite beds for designated water post-treatment. This is a Fundación Centro Canario del Agua, it's a Canary Island company. Also a patented process in order to eliminate fluorides in supply waters, because in Tenerife they have a big concern with fluorides in water. And finally, I will give an overview of the challenges that the islands, the water cycle in the islands will have to face in coming years. We'll have to minimize the carbon footprint, maximizing the energy efficiency, or making the direct or net balance use of renewable energies in desalination and of course in wastewater treatment plants also. Trying to apply circular economy principles in relation to the inputs of the process, reducing discharges into the sea, so brine valorization is a key point at this moment, reducing chemicals and promoting that valorization. Search for the lowest possible operating cost, new supply, rationality in the demand for surface area volume of occupation, and of course the security in its operation, and why not the adaptation to climate change, that means water reuse. I think that's all from my side. So thank you very much for your kind attention. Mahalo.
No, thank you very much. Great presentation, Juan Antonio. And the main question that we had from the audience was on discharge of the desal, and you covered it in your briefing, so I won't go over that. But I wanted to point out that one of the things that you focus on is decentralizing the desalinization plants, so you're not highly concentrating your discharge in any single areas. You're spreading it out pretty much across the coastline and putting it out far enough and dispersing it as well as treating it, as you say. So that's a really critical thing. The other takeaway I had from your presentation was Hawaii still relies on its groundwater lenses to get most of our potable water. And you mentioned that early on, maybe back in the 50s and 60s, you started getting saltwater intrusion into your fresh water. And that's because I think you're very similar to Hawaii in the sense that our freshwater lenses oftentimes are adjacent to saltwater. They're right next to each other. They're separated by their chemical boundary. But when you start to deplete the fresh water, the first thing that happens is you start getting saltwater intrusion. So we're a lot more like the Canary Islands than most people think. And thanks to these two presentations, we've gotten a really good glimpse of how they've handled it, and they're quite a couple decades ahead of us in terms of making things happen. So I thank both of you for your presentations and bringing us forward and showing what the technology can do, and also how the energy plays such a huge role in providing what's a requirement, which is fresh water. I told the presenters before the thing that in the military aviation side, when you go to water survival school, they say you can live several weeks without food, but you can only live 3 days without water. And water is a critical element for all of us to survive. So thank you both very much for your presentations. And right now we'd like to move to Barry Usagawa he's the program administrator for Water Resources Division at the Board of Water Supply. So Barry, are you ready? Do you have a presentation, Barry? Do you want to take charge of the screen? Okay, we'll do a share screen.
Thanks, Stan, and hello, everyone. A very interesting presentation so far. 319 desalination plants. I can see why the energy grid there is so diverse. Anyway, here's Hawaii's, or Honolulu's story on water. First, a little bit about the Board of Water Supply. We're a semi-autonomous city agency governed by an independent board of directors. So somewhat separate from the city, but we are a city department. We're the largest municipal water utility in Hawaii. We're serving about 1 million customers on Oahu. We deliver 145 million gallons per day of potable water and about 10 mgd of recycled and brackish non-potable water. Our service accounts are about 173,000 service connections. Our water system is integrated island-wide for flexibility and redundancy. It consists of 13 tunnels, 5 shafts, 194 groundwater wells and source pumps, which is distributed around the island. 13 treatment plants, mostly for pesticide removal because of legacy pineapple plantation contamination. 172 potable water reservoirs. We got a couple of non-potable recycled too. 192 booster pumps and 2,100 miles of pipeline, which is a challenge to ensure that main breaks don't disrupt levels of service. 21,000 fire hydrants and serving 1 million people, as I was saying. A little bit about our Oahu's water resources, groundwater. The board's water system is 100% groundwater. This is a cross section midway through the island. I think what Stan was saying, freshwater because of density sits over denser salt water. There's a zone of mixing there. This is all porous lava rock. And along the ridge lines of our mountains, we have high level water because of the dikes that exist there. But the source of the water is just rain. It all starts with rain. Rainfall in the ocean around the island is about 20 to 25 inches per year. It's the mountains that create the rain. Yes, the rain does follow the forest, but the mountains do create the rain. The Ko'olau Mountains are normal, 90 degrees to normal to the trade winds, and as the trade winds hit the mountains, it rises, cools, and condenses, and that's what creates the rain. So most of the heavy rainfall occurs on the Ko'olaus. The Waianae is drier, the west side, because it's in the shadow of the trade winds there. These are the water body, the groundwater aquifers on Oahu. The primary largest sources are in the central corridor, Wailua, Schofield, Pearl Harbor, and Honolulu. These are the largest, thickest aquifers. And they are about 700 to 800 feet thick. And the reason why they're thick like that is because of the cap rock, that sedimentary coral and terrestrial sediments that have accumulated when the sea level was higher. It acts like a dam that creates a thick freshwater lens, and that's what's in blue here, pretty much around the entire island. And that's why we have so much groundwater. Well, how much do we have? According to the State Commission on Water Resource Management, 393.5 million gallons per day is the sustainable yield of these 24 or so aquifer system areas. So of those natural aquifers, they cut it up into management areas for, and each one has a sustainable yield. So you wonder, well, will our sources dry up? No, because we are limited in terms of how much we can pump. And we cannot pump more than that. Otherwise, we start to deplete the aquifer. Climate change will affect the rainfall in the future, but we need to, so we're looking at that to see how we can make our systems more resilient, how we can enhance the recharge of rainfall into our aquifers and streams. In terms of population, our land use plan directs the growth to South Oahu, so Ewa, Central Oahu, and the primary urban center. What that does is it keeps the rural areas or the urban fringe areas, it keeps them rural. So all the growth is directed to South Oahu. And that's illustrative to us because then we can then focus our investment for infrastructure to the growth areas. Our plans center around our mission and vision statements. So Kawai'ola is our vision, water for life. Our mission statement is safe, dependable, and affordable water now and to the future, in that order. So safety is paramount, dependable, but it has to be balanced with affordable water. Our strategic plans updated every 5 years that keep us on track. And what you see around this wheel is all of the initiatives that we've been working on. If you want to talk about infrastructure or finance or conservation or energy savings, I can, but I want to focus on our watershed management plan because then folks asked me to talk about the Ahupua'a model. The Ahupua'a is the Hawaiian land division, basically by watershed from the mountain ridges to the coral reefs. And the island was divided into these Ahupua'a and managed sustainably for centuries before first contact. Almost 1 million Hawaiians were living in the state prior to the first contact. In short, the Ahupua'a is an environmentally holistic and culturally based sustainability model of land and resource management. Land we call Aina, water we call Vai. It recognizes the interconnections between Mauka and Makai. So what happens Mauka affects Makai. What happens above the ground affects what's under the ground. And we're carrying that model forward into the modern context by technology and this diversification and conservation and recycled water systems. So this is what one view of what our future could be, embracing the all model going forward. In short, the plan that the watershed plan is a plan for not just how much water urban and agriculture will use. It's also about how can we preserve and manage the conservation districts, sustainable groundwater and surface waters, and nearshore waters all have to be in balance. Cultural resources and traditional practices are very centered to the plan. And a plan cannot be an implementable plan if it doesn't include or behaviors or the social side or the cultural side. So the stewardship model is called Kuleana in Hawaiian, but it's all centered around watershed health. And this integration of resource management and land management provides this holistic Hawaiian watershed model. The plan goal is to formulate an environmentally holistic, community-based, and environmentally viable watershed management plan that will provide a balance between preservation and management of Oahu's watersheds and resources, and the sustainable use and development to serve present and future generations. It has 5 objectives: promoting sustainable watershed, protecting and enhancing water quality and quantity, protecting Native Hawaiian rights and traditional customary practices, facilitating public participation, education, and project implementation, and all trying to meet future water demands at reasonable costs. Each of these elements of these objectives come with specific strategies and policies and projects in the plan. It's a regional plan. There's 8 of them, will be 8 of them, island-wide, to ensure that we are in balance and that we are sustainable given the issues around watershed management, water conservation, this whole diversification of water supply. Even though we're 100% drinking groundwater for drinking, we have the largest recycled water system in the state, and we're just in the procurement stage of a small seawater desalination plant in Ewa. And then we also are looking at climate change adaptation, because the sustainable yields and the rainfall is looking to change in the future, and we need to understand that. And sorry, I'm at 10 minutes. So just wanted to say the conservation has been successful. We've reduced our per capita demand from 187 to about 150. I think it's about 150 gallons per person. So we are more efficient. Our climate models from the UH is showing a dry and a wet future. So we have scenarios. If our future is dry, then what are we doing about it? And this is where the Canary Islands example is telling, because we really have to get our per capita down to 100 gallons per capita a day and diversify our system more. If we're in the wet future, we just continue to with business as usual. We did calculate sustainable yields in a low and high. Don't want to go into that, but just to letting you know. And I want to finish with our one water approach to the water, to ensuring that there's sufficient water supplies going forward. All types of water. Its integration of one water is basically surface, groundwater, stormwater, recycled, conservation, energy, water, energy, and collaboration. And this is my last slide. I believe we have an ordinance that has institutionalized collaboration around this one water framework, identifying the multi-benefits between water and wastewater, basically reuse and infrastructure and stormwater capturing, green infrastructure, as well as how we would adapt to climate change. So with that, I just want to ensure that the water services, we need to make water conservation a way of life. If we treat every drop like it's our last, we'll be able to conserve it and sustain ourselves into the future. So thank you very much.
Thanks, Barry. You hit pretty much all the questions that we had on our list. So I thank you for a great presentation. And if there's any more from the audience, we can pull them up. But I'd like to get Manfred up and give him a chance to get his presentation done too. We're at the 10 o'clock time frame. I think we have a little bit more time, but I'd like to keep pressing on. So Manfred, if you're ready, you can bring your screen up and hit it. Thank you.
Well, thank you, Stan. Well, it's a difficult task to go after this three nice presentations. So I will be doing something very basic. We spoke in our group here, because sometimes, it's getting overwhelming with so many technologies. So I'm actually doing only 2 potential solutions to the water crunch. And again, we're also doing some work on the mainland, on the Southwest, where we are not as blessed with water as here, but the problem with water will be around. So today I'm going to, let me see here. Sorry about that. So today, actually, I'm just speaking about 2 things. And let me just also start So I will be speaking about recycled wastewater to lower the potable water. Barry already suggested, Board of Water Supplies looking into that. Canary Island is looking at it. It's very good. The second one, which I'm also very interested in doing some work, is actually to increase the use of digital tools in the water supply infrastructure. So we can actually avoid unnecessary losses. And that will be data sensing and digital twins. So I'm not going into a lot of details. I'm just wanted to point out what actually are the possibilities. And again, these are only two possible solutions. Again, Barry was saying all these things actually with board of suppliers in the. So here actually, it's an illustrative case. And I use the EPA, number of 400 gallons per day per family. Again, it's everywhere. It's the same. Hawaii is a little bit more, for instance, than in the Southwest. And where we are having some work in Las Vegas, they're about 85 gallons per day. And here we have right now, we're saying about 200 or whatever. So let's say right now we have 400 gallons per day is coming to our doorstep. And we usually have a 20 to 35% of supply losses, like leaks and so on. So we have to put into the pipeline, which comes out afterwards at our house, about 540. So the 400 is actually from the 400 gallons per day. We have outdoor uses and indoor uses. Let's say we have 30%, EPA say 30% is outdoor landscaping. Again, this is all average, and we have 70% of indoor use. So that's actually right now here on the left, on the right side, this is actually that we can using recycled wastewater to lower the potable water use. On the left side, we can upgrading digital tool in order to drive down the losses. So that's what we just touching right now. So next one, actually, what is the normal conventional water and wastewater system, which is, right now most likely done here. And also otherwise, we have potable water supply comes into our buildings and it is used there and we are discharging into the sewer. And the sewer ends up at the central wastewater treatment plant. And from there actually goes into the ocean or receiving waters, what we call it right now, the water which receives the discharges. So that's a central, this is the typical scenario. So the other one is actually which Board of Water Supply already uses a little bit, that we have like a central plant, a central recycling plant. So we take some of the wastewater which is going through the sewer and treating in the central recycling. And usually you have point sources, like you can actually use it in watering golf courses or agricultural things right there. And we saw that Canary Island has already some kind of distribution. So this means if to make this scenario work, we would actually have to put a long distribution, basically two lines, close to each other, the water supply and also the recycled water, in order to make it work in a larger system. So what could we do? Right now, we could actually have what is on-site wastewater treatment and reuse. This means actually we would be treating the wastewater on-site. So we would avoid, long distribution lines. It's also in terms of energy right now. We're working with the EPA just, on a grant. How do we actually, cover, lower the electricity demand? Because otherwise we have to pump a lot of water back and forth, wastewater and so on. So in this scenario, would be the on-site wastewater treatment and reuse is that we are treating the water on site. So distribution is very short. It's just, going, from the treatment, on-site treatment to our own garden, or for instance, toilet flushing, whatever we can use the specific reused water. Is it an issue for Oahu? And in this slide, actually, we see the on-site wastewater treatment system in Hawaii. The red areas is where we have a lot of on-site wastewater treatment system. And the reason is that, sewer system is not everywhere. So that we still have to, there's a lot of on-site treatment systems. So the potential of just transferring it or converting is there and real. When we look at the wastewater right now, I just wanted to see, what is the paradigm we are operating under. So it started like in 1700 before Christ, and there was the first water closet in Crete, and that actually was the goal of keeping the wastewater away from people, then actually to secure public health. And then in the 1970s or so was actually coming more like we not only have to secure the health of the individual, of the public, but we also have to look into environmental resources. So we have to protect it. So that actually came as and that's why and you see the arrow down here, that's probably in A and B, that's where we still are. We actually are only dipping our feet right now in you're seeing that actually the wastewater can also be like a valuable resource. So what are we doing with the effluent in order to make it valuable? So right now I just have to give you an idea what we still have here. A, B, and C on the left side, securing public health. It's, we have a cesspool. We actually have a cesspool problem. And that is like, we have, this one is the only thing, just getting wastewater out of the house and put it underground. But the environment is not protected. Under B, actually, we have what we call the conventional septic systems, which probably everybody has heard of, or aeration systems. These are on-site wastewater treatment. But septic system is mostly just getting out of sight. But it's better than its cesspools. And on the right side, the C is effluent, fit for human use and consumption. This is actually right now where technology development is really, kicking in. There's a lot of technology which can be used. And again, there are a lot of advantages of keeping the wastewater treatment on site. Again, it's much easier to reuse it. So let me just go over right now very quickly what actually it is, what we have right now in terms of on-site wastewater treatment plant. We have the cesspool. This is basically a hole in the ground, where we put our poop in there, and it's either held or just it can leach out into the field. You see here 350. This is BOD 5. That's actually an indicator of organic pollutants. The higher this number is, the bigger the organic pollutants is. So we have made a strive here in Hawaii just to convert that, but you see, we just, it's supposed to be, cesspools are all supposed to be done by 2050. So there's some urgency, but it's a pretty long time horizon. There's a conventional septic system is better, where we have a tank, and then afterwards from the septic tank actually goes into a distribution field. And here, see on the numbers here, it comes in at 350. The effluent of the septic tank is 150, so much better than the cesspool. And then actually what comes out of the drain field, because there's also some treatment ingoing, is about 40 to 60. The problem is we cannot really verify. We don't know. It could be failing, could be very high BOD going into the groundwater or not. So another one actually is already refined is an active, way of treating it on site, where we have activated sludge, meaning there's a lot of critters, eating the organics up. And then you have activated sludge. You have to do a lot of aeration. Afterwards, it gets into what we call, just a final sedimentation. It's a clarifier where we separate the particulate to soluble, pollutants. And then afterwards, it usually goes into a subsurface infiltration field. And if you look here right now down here, so it's actually the nice thing that we can see, it comes in 350. And the process tank gets out at 50. What comes out of the drain field should be about 30. But again, like what comes out of the drain field, we cannot really tell. So the last one under C, what I'm also working right now in a couple of, in one large pilot project here in Hawaii is use advanced wastewater treatment with the so-called MBR, a membrane bioreactor, which actually also is treating it naturally by activated sludge. And then, but the big difference is that it goes through a membrane. So it takes out a lot of most of them. And you see it comes in at 350 BOD and it goes out at 2 or 4. So it's very, very good water which comes out. And by the way, actually right now I look back in the EPA in the 90s, they changed it. The amount of what the water coming out of the MBR would be suitable for swimming in that at the EPA in the 1990s. Then afterwards they have, in terms, it's not only organics, but pathogens is coming down, nitrates, all that kind of stuff is really amazing technology. It's getting mainstream and it can be done. Just to give you an idea where we are right now, it's like we're doing we have been doing some work with regulatory agencies here. The problem right now is that actually there is no real standards available. Look at this lower, diagram where you see septic system, conventional aeration system, and MBR system. These numbers, 150, 40, or 4, indicates what actually would go into the subsurface soil disposal field or leach field, what a lot of people say. Right now, actually, we have to use the same size, whether or not it's a septic system, if it goes 150 BOD in, or for instance, in the MBR4. That's actually right now, this is, so we don't give actually the technology the due advantage and benefit. So there's a lot of things which we have to still do in order to come, just to implement the technology which is around. Here, very quickly, there's a great study, and it shows the divergent views of agencies and technology experts. You see in black, this is the regulatory side, and the gray is system side. So for instance, in terms of health risk, the agencies think it's much bigger deal than the system side, so it's engineers, technology, the provider, and so on. You see the difficult to manage is way, they think it's much more difficult than the technology guys are. Expensive, both it's about the same, although right now we can actually create a lot of benefits to that. So it actually comes out cost neutral. And then it goes down, and right now under 8, the reduced potable water demand, both actually about 80% of regulatory, the 89, almost 90%, they agree. This one actually would be good in order to reduce potable water. Then actually we spoke about energy. The technology side is much more optimistic than the regulatory side. So right now, the biggest barrier actually of introducing it is most likely regulatory side. It's not so much cost side. All right, so when we look actually what is possible, and just go very illustrative. So let's say we actually do the following, still the 400 gallons per day of what comes to your footstep here in the building. So the first of all, actually, we can cut down by improving leaks in the supply system, other inefficiencies. And then when you see here on the right side, what is inside use 180 gallons per day, outside, recycled indoor and outdoor use would be 140. So you basically, you cut down the potable water supply from about 500 to about 220 in this illustrative, example. So potential savings are huge. And actually, we could actually take this into our. So the second one, very quickly, very high high level digital tools in the water industry. So I'm not really, aware of what Board of Water Supply does here. I've been doing some work with what is called digital twins. So there are facts. Digitization is fast increasing also in the water industry. It will manage all aspects. And right now you see an amazing acceleration of the technology. Like digital twins have been around for a couple of years, but right now the use actually is increasing very fast. And the aim is actually to optimize the design of the infrastructure. And when we speak about, advanced modeling and digital twins, on the left side is like the technology development. I've seen I have some colleagues there right now, they used to do everything in terms of physical modeling or whatever. Advanced modeling like CFD and all kinds of stuff, which we can use is amazing. So it cuts down on the technology developing side, the cycle. And on the right side, when it comes to operation maintenance of infrastructure, the digital twin is actually, probably almost likely, one of the big technologies in the future to use when it comes to cutting down on cost and also energy and so on. Very quickly here is like, what is a digital twin? And a digital twin is a virtual replica of physical asset that is updated in real time and representative of its proven characteristics. It's a handful of words. Basically, like you have a physical assets and then you model all kinds of characteristics in the digital twin. So you can actually not only like in the building information system, you used to know what is in the building, what is available. The nice thing over here in the digital twin is that you can run scenarios. You can actually simulate what happens if there's like a water break. What actually you can see why it's in a certain area of the city or whatever. Why is actually the demand so high? And there has to be something going on. So that's basically it. The digital twin, 5 elements. And you have, first of all, the geospatial physical data, where actually things are, and you have like real-time measurements. So that actually feeds in your digital twin. You can see in historical data what actually was the performance looking back. And then the analytics, that's actually the engine digital twin it can really simulate and tells you, hey, what happens if, what happens if, for instance, like, we have to put these particular wells off because, one of the Red Hill actually, is worse than it's supposed to be. And then digitization, that visualization is like the operators are inundated with data that actually gives you, an idea of where are problems. You can see how do they, for instance, pumps, how do tanks, what are they behaving, how should they perform? So I just, hopefully it was not too fast. Stan, thank you very much. And that's basically my presentation. So if you have any kind of question, you can just follow up.
Thanks, Manfred. Thanks, Manfred. Eugene, and if you could stop sharing, then we'll let Eugene pull his slides up. And we'll wrap up today's discussion with Eugene. And, Manfred, the digital twin thing seems a lot like what the military uses for aviation simulation, where you can actually do more in the simulator to simulate emergencies and figure out what happened in accidents by using that digital twin model.
It comes from there, right?
Yeah.
Yes.
So Eugene, are you ready?
Yes, I am here.
Okay.
So
take it away.
I assume you see my screen. Let me start from the beginning. Let me see, I couldn't make it. Let me, it doesn't show the screen is going.
It's up. If you go to the bottom right and push on the little image of the screen down in the lower right corner of your thing, it'll go to a presentation mode.
Let's see, let me try that again. So it will be.
If you look right at the bottom of your PowerPoint presentation,
Okay.
where it says a minus, and then there's a dot and a plus and 105%. Right next to it looks like a little pull down screen. If you click that, that should put you in a presentation mode, and then when you just scroll through, it'll change your slides for you.
Right. I did do that, but it didn't go. I don't know why.
Not working. Okay.
Yeah. So yeah, without showing my presentation is pretty short.
Well, just give us the verbal then, and we'll try.
I
and
think
follow.
Eugene can just along the left-hand side, just click on the slide.
The
and
slide.
it'll show
Yeah,
up.
that's true. That'll work too.
Right, but it didn't go anywhere. It does. It's stuck actually.
Oh, okay.
Yeah, I don't know why it is stuck.
That's okay. Just breeze through it.
Yeah, let me try one more time and see maybe. Yeah, it doesn't go anywhere. I don't know why.
Okay.
But Mike wanted me to talk about the body of water, and it came to my mind right away is the everybody study economic class, economic course. You would have something called diamond water paradox, which is actually started with the birth of the economic theory in 1776. That reminded me that next week, and it will be the 4th of July. In 1776, there are two things happened. One is the US became a country, and the second is the birth of the economic theory. So basically, the value or the price of water is much lower than the diamond. So that was a dilemma for Adam Smith in 1776. But 100 years later, in the 1870s, there were a few economists found out that, yes, it's because when people have that in economics we call the utility, is the happiness or satisfaction. When you have the second or third, when you have water, the first bottle of water is valued high, but when you have the second and third, the value decrease a lot. But the value for diamond doesn't decrease much. So that's why the diamond is very high value. Water, the value in terms of price is lower. It also has something to do with the supply. But the number I wanted to show is actually the total demand or consumption in Hawaii. So basically, it shows a declining trend. I think Barry has showed that already. It has been declining for all the counties, all the 4 counties. And if I calculate from per capita in terms of the de facto per capita, that means including the visitors present each day, we have about 250,000 visitors each day on the island. And we also have people traveling out of state. So including the people on a typical day on the island. So we divide the total water consumption by the total de facto population. It also shows that it's declining for all the counties. I think the declining also is mainly due to the efficiency use and the management by the water supplies. And I also calculated the productivity of water. How do we calculate that? Is we divide the total GDP by the water consumption. It shows everything else, if we keep constant, the water contribution, or maybe when we produce $1 of GDP, how much water we need is also declining. That indication of the improvement in the water productivity. And my last slide actually shows 10 years apart in 2010 and 2020, who are the top users of water. So mainly in 2010, the major user for the water is actually tourism industry, the hotels. But in 2020, the major user is actually the golf course. So it's also related to tourism. Beyond the tourism, there are government, federal government, and county, state and county government, and also the refineries. Both the 2010 and 2020, the refineries, they also on the top 25 list in terms of water usage. I think that is what I was planning to present, and that concludes my presentation.
Okay, Eugene, thanks. That's a surprise that the refineries actually use a lot of water. I was not aware of that. We didn't have any additional questions come in on chat that, and thanks Barry for covering that one question on whether we need to drill more wells. I appreciate that. That does it for our presentations and Q&A, and I'd like to turn it over to Michael Markrich for final comments. And thanks to all our presenters again for doing a great job. A lot of great feedback on especially on the presentations from Canary Islands. Outstanding, and we're hoping that we can share that at least in the recording, if not taking your actual presentations and providing to folks, because there was a lot of great information there, and also on Barry's and Manfred's slides too. So Michael, I'm going to turn it over to you for last comments.
Yeah, I want to thank everybody for excellent presentations and for bringing light to this very complex issue that's so important to all of us. And so what we're going to do is we're going to post the information as soon as we get it. And so all the slide presentations will be available. And I hope that in the future, we can continue this conversation with the Canary Islands. And we look forward to speaking with you all again. And Barry, thank you very much for all the hard work the Honolulu Board of Water Supply does. So thank you. And Eugene and everybody, thank you. So until the next time, rebuild Hawaii, aloha.
Mahalo. Aloha.
Aloha. Juan
Aloha from the Canary Islands.
Dr. Garcia, thank you.
Yeah, and thank you very much for your kind invitation.